Welcome to section 7.9. This section is entitled Conditional Probability and the Multiplication Rule. So this is going to extend us a little bit farther in our study of probability. So far we've learned basic probability. We've looked at some odds associated with that. We've also looked at the OR probability. And then this is going to extend us a little bit farther as we looked at conditional probability and what they're going to call the multiplication rule. So let's start out with conditional probability, and I already typed out a definition so that it'd be easy to read. And this is just my definition. The book will have a different one that may resonate with you. But conditional probability is finding the probability of an event occurring given a condition has already been met, right? Some other condition. And so let's take something that we know really well. Let's take rolling a single six-sided die, right? And we're going to ask this question: find the probability that you roll a 2, right? So this is coming right back to our section 7.5, I believe, where we're finding just a basic probability. Well, we know how to do that. We know what our sample set looks like from 7.4. And you don't have to write this out every time, but I just want to make it as visual as possible. We want to find the probability of rolling an outcome of 2. So we just look at the 6 outcomes that are there and say, well, any one of these 6 things could happen. One of those is the number 2, so my probability is simply 1/6 as we look at that. So nothing new there. Then we did some OR probability, but let's talk about this conditional probability. The question now is going to be a little bit different. We're still going to roll a single six-sided die. So this was question 1. How about number 2, this question? Find the probability of rolling, that you roll a 2, I'll keep it the same, given the outcome is even. So take a pause there, because what was added was that last part, but really specifically this word right here, given, is the one that tells us we're dealing with conditional probability. So we have conditional probability. Some condition is given, and whatever comes after the word given, whatever phrase comes after that, is what we absolutely know has happened. So if I go back up to my definition, find the probability of an event occurring, getting a 2, given a condition has already been met. So given the outcome is even. So if you look at the top of the screen, I have all the outcomes possible when I roll a die. But here's what the given is telling me. Hey, you know that you're just looking at even numbers. So the even numbers on a die are just 2, 4, and 6. I know that an even number has come out. How do I know that? Because it comes after the word given. So what is known as the outcome is even, and the question is, if I knew that, if I knew the outcome was even, what's the probability that I roll a 2? Well, let me show you some notation. The probability that we roll a 2, given that it's even. So this little, not horizontal, but vertical line here, this vertical line here is the word given. So you'll see the book use these symbols as well. Hey, what's the probability that we roll a 2 given the outcome's even? Oh, well, there's only 3 even numbers, one of which is a 2, right? So our sample set is much smaller. So a conditional probability limits the focus that you're seeing. It's only on a very limited scope there. So hopefully that's making sense. Let's look at another example that they do in the book and in the homework as well. And then we'll get to some other examples as we go through and look at this idea of given probability. So we could look at continue with the die example, rolling 2 dice. How about 2 4-sided dice? And considering the total. I'll put the sum here just to keep the language of the book consistent. Okay, so maybe it would be good for me to see my space. And so I have 1, 2, 3, 4, 1, 2, 3, 4. Could come out on either die. So again, I'm looking at the total. So my total is 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7. And then 4 is 5, 6, 7, 8. And those are my totals there. And so we can ask this type of question. Hey, what's the probability that I roll an even number given, right? Remember this little line means given, that you know a 5 has been rolled. So what's the probability that I have an even number? Apologize. Not given that a 5, I was thinking about a 6-sided die. Given that a 3 has been rolled. We'll make it, so you roll it, and what's the probability it's even given that, maybe it would be better states, one of the dice has a 3. Okay, so we want to know if it's even. So one of the dice having a 3 is isolated between this column and this row. We know that a 3 has been rolled. So it could be either one of these. We didn't say which die it was, so we have to consider both of them. And we want to know what's the probability that the outcome is even. Well, let's first get our bottom number. There's 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7 different totals that could come out. We do not want to count this 6 twice. 7 different totals that can come out. 4, 5, 6, 7, those 4, 4, 5, 7, those 3. Right? And out of those, how many are even? There's 1 even total, 2 even totals, 3 even totals. And so my answer is 3 7s. So pretty interesting in there. They'll play around with this type of chart and ask us to do different things. So they could say something like, hey, what's the probability that it's even given that it's greater than 7? Okay, probability that's even given that let me make this a little bit more clear, given that the total is greater than 7. All right, cool. Let's first identify the totals that are greater than 7, and there's only one. This number 8 down there, but that's not my bottom number. Sorry about that. My bottom number is 1. There's just one number greater than 7. So I know it's that number. Is that number even? Yes, that number is even, and so the answer is 1. So pretty interesting there. I'm going to keep this space open, so hopefully you're okay if I just erase these things. You can always back up the video. But again, out of the one thing present in my sample space, because I know it's greater than 7, only one of those totals is greater than 7, what's the probability that it's even? Well, it is even, so it's 1 over 1 or just 1. It's a sure thing to happen. Let's reverse that a little bit. What about this? What if I said the probability that it's greater than 7 given that the total is even? Okay, well, I just have to look at my even totals. 2, 4, 4, 6, 4, 6, 6, 8 are all my even totals. So my bottom number will be what's in my set. So in my set, I have 1, 2, have a 2, a 4, another 4, right? I have all these different even numbers that can come out. So 1, 2, 3, 4, 5, 6, 7, 8. There's 8 even numbers. That kind of makes sense. Half of them are even. 16 outcomes, half are even. Now, what's the probability that it's greater than 7? As you look at those circled numbers, which are in my sample space, how many are greater than 7? Just 1. And so instead of, the other way it was 1 over 1, here it's 1 over 8. So pretty interesting in there. They do a lot of work with cards. And so they could say this: if when one card is selected, find the probability that you get a king. And then what makes it this section is this word right here, given the card is a heart. Okay, so symbolic wise, that would be the probability that you get a king, given you have a heart. All right, so let's think about our deck of cards. What do we know about our card? We know what's ever after the word given. We absolutely know the card is a heart. So that's where we start. So whenever you see this word given, you're going to say, okay, what's my base? Your base is what always comes after the word given. The base is always what you know, which is after the word given. You know the card is a heart. So even though there's 52 cards, with conditional probabilities, it's telling you, oh, it's not all 52. You're only looking at the 2 of hearts, the 3 of hearts, the 4, 5, 6, 7, 8, 9, 10. And then I'll come up here, Jack, Queen, King, Ace. You're only looking at these hearts. You're only down to these 13 cards, right? If we count those up, there's going to be 13 different cards. We know that from our work from before. And the question is, as you look at these 13 cards, how many are kings? Only one of them is a king. Sound all right? And so we have this pretty nice, let's see. We have this pretty nice first process to go through here. Sorry, that was a little bit of a delay. What if I did something like this? The probability that it is a diamond, given that it's a jack. Okay, so we think about our deck of cards that has all these different cards in it, and we recognize that there's suits, right? So we have the hearts, we have the diamonds, we have the spades, and we have the clubs. So we have those 4 suits, and each one of them has the numbers 2 through 10, and then the Jack, Queen, King, Ace. In particular, we're concerned about the jacks, and we know that there's 1 in each one of the suits. There's a Jack of Hearts, a Jack of Diamonds, a Jack of Spades, a Jack of Clubs. No other cards are jacks, so remember, this is the denominator part. We know the card is a jack. So there's only 4 jacks. What's the probability that the card you pick is the Jack of Diamonds from just 4 jacks? Well, it's the 1 Jack of Diamonds out of the 4 options. And we're doing just great. And so everything should be visual. They'll often go and look at the same chart. Remember this chart from previous sections that gives the majors as well as the years. And so they'll just take this and say, well, let's ask them some conditional probability here. What's the probability that you are an arts major given that you're a sophomore? So given that the student is a sophomore, what's the probability that they have an arts major? Well, that's not bad at all. It's totally structured for us to answer this question. What we do know is that we're only looking at sophomores. We're only looking down this column right here. We're isolated to that column. What do we know? That there's 770 students in that column. What else do we know about that column? We know in that column only sophomores. We want to know how many of those sophomores majored in the arts, and we can see that in the very first row. There's 121 students that are sophomores that have majored in the arts. So that is our probability, 121 out of 770. If I want to know the probability that the student is a senior, given that they're majoring in social science. Well, great. What do I know? I know that they've majored in social science. I'm not looking at anybody except those that have majored in social science. The way that this chart is given, it tells me that there's 555 majors in social science, right? We can see that right at the end here. Right, that 555 is the total. So focusing on this row, and that's when it's given in a column and rows like this in a table, we can usually just isolate to a row. We wouldn't be able to do that if it was more complex, but most of the time it is just isolated to a particular row. And then the question is, in that row, in those 555 social science majors, how many are seniors? And I can just look under the senior column, 132 of those 555. The 132 of the 555 are going to be seniors. And so that's the probability that we randomly select a senior given that they're a social science major. So pretty awesome. That is conditional probability. But there's a second piece to all of that as well. So the second piece is what they were calling the multiplication rule. And as you think about this multiplication rule, I'd like you to understand it a little bit more. This is the probability of two things happening in successions. So what you'll notice is that there are multiple picks. And I think our book isolates it to just two, but we'll see if that's different. But it's the probability that two things happen in succession. So there's a problem in the book, and what they're going to give you is something like this. They're going to give a die, and on that die, so you're going to roll a 6-sided die that has sides. One A, one B, 2A, 2B, 4A, 4B. Okay, just a little bit different than what they have for those first homework questions, but very similar. They're going to ask a question like this. Find the probability that if you rolled the die twice, you would get 2 vowels. Okay. So, I didn't need to put a hyphen there, but that's what we're being asked to do, is find the probability that we get 2 vowels out. So we know what vowels are, A, E, I, O, U. They've been using that those languages of vowels and consonants for a little bit now. And so we're a little bit familiar with that. So we want to find the probability that we're going to roll the die twice. It's this twice that kicks in this multiplication rule. And essentially you handle it one roll at a time. So take a look at your sample space. We're trying to find the probability that we get a vowel on the first roll and then a vowel on the second roll. All right, so as we roll the die, we're going to handle this one at a time. We're going to do the first roll and multiply that to the second roll. That's what happens if you have things happening multiple times. If you look at all of our questions previous, it was selecting one card, rolling a die one time, rolling a pair of die one time, and looking at the total. Now we're going to do things twice. And so pretty easy. And if we did it 3 times, it would just extend to one more multiplication. So one roll at a time. We roll the die, and we want to know the probability it's a vowel. Well, there's 6 sides. You can see those sides up here. And I'll go and point to where I'm looking. And we can see the different sides that can come up. So there's 6 unique sides that could come up. And the question is, what's the probability that a vowel comes up? Well, let's go find out. So let me change this to red color. Here's a vowel, and here's a vowel. So the probability is 3 out of 6. So what's the probability when I pick that die up again that I would also get a vowel? And so I roll it again, and there's 6 different outcomes, 3 of which are vowels. Nothing changes because the events are independent of one another. What happened on the first roll does not affect what happens on the second, mainly because as I roll that die and something comes up, I pick that die up again, and I haven't lost any of the 6 sides. All 6 could come up again, and 3 of them are vowels. And so we multiply these. 3 times 3 is 9. 6 times 6 is 36, right? So it could be left just like that. We could reduce it down to be 1/4. Okay, so that's what we're looking at as you go and answer these questions. They'll ask this. They'll say, find the probability that you get 2 odd numbers. So when probability of rolling 2 odd numbers. Okay. Well, if we look at this, as I go to roll the die, there are 6 different outcomes. Now I have a different focus here. I'm no longer concerned about a success for me is no longer getting a vowel, is now getting an odd number. And so as I go to circle, 1's odd and 1's odd, but everything else is even. So 2 of them are odd out of the 6. And that's going to be the exact same fraction here. 2 times 2 is 4. 6 times 6 is 36. And so we get a 1/9 coming out of there. So that's what we're dealing with as we go to this multiplication rule. And you'll see something very similar as you look at these tiles. Let's go back to the cards. I want you to picture a 52 card deck. And I'll change back to a black color. So we're going to look at a 52 card deck, and we're going to select 2 cards from a 52 card deck. We're going to look at a few questions together. We want to find the probability that they are both kings. Okay, let's do that. Well, if we remember our process, we want the probability that the first one is a king and the second one's a king. But we're going to do it one at a time. So if we picture our 52 card deck that has the hearts, the diamonds, the spades, and the clubs. And in each one of those has 2 through 10 and the jack, queen, king, ace. 2 through 10, Jack, Queen, King, Ace, right? All these. And we're just going to make it as visual as possible. We have all those cards. So we went under the probability that they're both kings. So when we first go into that deck, we have 52 cards that we could choose. And so we know our bottom number is 52 by our work back in the earlier part of chapter 7. There's 52 cards. How many of those cards are kings? 4 of them are kings. Now I have that card. I don't put it back. So unless it tells me, we go with the natural thing of don't replace the card. So I've been dealt a card, and it is a king. Now I want to know what's the probability that I get a king. So watch pretty carefully. I'll do it in red so it's not just a quick erase. We just selected a king. We don't know which one, but I'm just going to cross one of them out. It's gone. So what's the probability that I get a king now? Well, you can easily see that I have 3 kings left. And that red card right there is gone. So let me go ahead and erase it. So that king is gone. And so now there are only 51 cards in there. And so I get 4 out of 52 times 3 out of 51. And so what would that be? That would be 12. 52 times 51 would be 2652. 12 over 2652. We see if 265. I can divide them both by 4 and get 663 over 3. And that does seem to reduce into 1 over 221. Might be what they have in the back of the book. So let me do 2652 divided by 12. Yes, and it comes out to 221, just to check that answer. I hadn't done that before. But very interesting. So this second fraction changed because they're not independent of each other. When I selected that first card, I removed both a king and an overall card from the deck. So things changed. It wasn't independent like the die was. If I keep this same picture in mind, what if I asked for the probability that I get 2 hearts? Right? So maybe I'm playing poker and I already have 3 hearts and I get 2 more deals in order to make my 5-card hand, and I want to know what's the probability that I'm going to see 2 more hearts. Okay? But I guess that's not our situation, though. What we are doing is we got all 52 cards, and we want to know the probability of getting 2 hearts. So what is that? Well, as we look at this deck of cards, 13 of the cards are hearts. So 13 out of 52 is the probability that I'll get a heart on that first draw. Now what's going to happen on the second draw is I'm going to have one of these hearts. So just make one up because it's only for visual purposes. Let's suppose that we got the Jack of Hearts. That's the card that we got. So remember, that's gone now. So now when I'm making my selection, it is out of 51 cards because that red card doesn't, that red circle thing over the Jack, it doesn't exist. That Jack's gone. So how many cards are left? Only 51. How many of those are hearts? Only 12 out of the 51 are hearts because the Jack was taken away. And then we run our numbers there, right? 13 divided by 12, or 13 times 12 is 156 all over the 2652 number. And then we can reduce appropriately. But that's what this process looks like when we have multiple picks. We just take it one at a time and really talk ourselves through it. Okay. Taking a look at the other problems that are here, they're very, very similar to what we've been doing. There is a problem where they have something like this, A, X. So they have these Scrabble tiles. And so it's not the exact same set that you'll do in the homework, but it's very similar. So we can do the process. So they'll say if you select 2 tiles, these are Scrabble tiles, find the probability that, and just looking at what they're asking, they are both consonants. Okay, sorry about that. So you want the probability that the first one's a consonant and then the second one's a consonant, right? Just to give you some different notation that may be helpful. What you know is that with 2 selections, right, 2 tiles, you're going to have 2 fractions. And you worry about them one at a time. So first of all, let's see the size of our set. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tiles. So we have 11 total tiles in our bag. And we grab one tile out and we want to know what's the probability that it's a consonant. And so if we go and circle the consonants, we find that the consonants are the non-vowels. We have 1, 2, 3, 4, 5, 6. 6 out of the 11 are consonants. Now, it didn't say to replace the tile. So you'll read sometimes they say, hey, with replacement. If it says with replacement, you look at that tile and then you assume success, right? I haven't said that, but you assume success as you go this way. But you look at that tile and then put it back if it says with replacement. So your fraction would stay exactly the same. But in this case, we lost a consonant. And again, for purposes of visualization, let's just assume it was the C and I'll erase it. Now when we count to see how many tiles we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not surprising, we lost 1, so we have 10. And we also lost a consonant, so it's 5 tenths in there. And so that's how we're going to do this type of problem. They have another one in there, and we need to see this build up because it's important. I was thinking that we had exhausted all the answers, but we haven't. So, or all the questions, right? So that you're exposed to everything that you're going to be asked in the homework. I'm just getting rid of some marks that I made here. And then we'll go put in what was here. This was a C, that's an E, and this is an NTX. So here's our list of tiles. What about this? The probability that the first one is a vowel and the second is a consonant. That's a very specific question, and they do ask it this way. So what's the probability that we get a vowel? Well, we already counted. We knew there was 11 to start out with. And this is without replacement again. So as we focus on a vowel, so in this case, let me go and change my color to blue. So let's focus on a vowel. There's 1, 2, 3, 4, 5 vowels in there. So 5 out of the 11 are vowels. And we need the second one to be a consonant. So all that happened in there is we lost a vowel. So we wouldn't move forward unless we were successful. So let's suppose we got that first A. Well, how many are left? There are 10 tiles left. And out of those 10, how many are consonants? Well, 1, 2, 3, 4, 5, 6 of the 10 are consonants. Then we would do our multiplication. That's 30 over 110. Or if we divide each by 10, that's 3 11ths coming in there. Again, either answer is fine, but actually do the multiplication. So it's got to be some variation of those right there. Last question. Okay. And this one's a little tricky, so that's why I want to look at it with you, because it does come up in the homework. So I'm going to erase above here so I can stay close to these letters. Actually, let me make up a new set, realizing how messed up those were. So let's suppose we have these letters, A, B, C, E, F, G, O. Let's suppose we have those 8 letters. They're going to ask this question: what's the probability that you get one is a vowel and one is a consonant? Okay. Here they're not specifying order at all, and that's the tricky part. This could happen in 2 ways. You could get the vowel first and then the consonant, or you could get the consonant first and then the vowel. Order does not matter. Up here they told us we wanted the first one to be a vowel and the second one to be a consonant. So as we're looking at this guy, we can be in any order, and so we do them separately. And remember what OR implied. OR implied that we add them. So what's the probability that we have a vowel? Well, again, there's 8 different letters that I'm looking at. How many vowels are there? There's 1, 2, 3, 4. 4 of the 8 are vowels, and then I need the second one to be a consonant. Well, that's after that first pick has happened, so now there's only 7 tiles left. And out of those 7 tiles, there are 4 that are consonants. Vice versa, if I look at the consonant happening first, there's 4 out of 8 consonants, and then 4 out of 7 vowels. It's not unusual. In fact, I think it almost always happens that the products are the same, and we're just adding them up. So 4 times 4 is 16. 8 times 7 is 56, right? And so we have 16 over 56 plus another 16 over 56. If you remember your fraction addition, you need those denominators to be the same at 56. 16 and 16 is 32. So we have the raw answer of 32 over 56. And I think both are divisible by 4. And so 56 divided by 4 is 14. 32 divided by 4 is 8. And those are divisible by 2 again. And so 8 divided by 2 is 4. 14 divided by 2 is 7. So that just tells me that I missed that they were both divisible by 8, right? And I should have seen that, but I didn't, and that's okay, right? All that matters is we get to that eventual answer. But if they're not specifying an order, you have to account for the fact that it could happen in multiple ways. And so that's what's happening here. That I wouldn't be locked into just getting a vowel first. It could be the consonant that happens first. But if it's the vowel that happens first, then a consonant must come second. And if it's a consonant that happens first, a vowel must come second. So take a look at all of that and then go and try the homework and see. I think you'll find it to be very close to what we've done here. And so hopefully you'll be able to refer back and do very, very well. Thanks for watching.